Hello everybody, hope you're having a good day today. And today we're going to be going over a projectile motion and kinematics. And so today's going to be kind of a video where there's going to be a lot of information, and I'll probably have like one or two practice problems at the end. But I'm planning on next video doing a lot of practice problems, as projectile motion can be confusing and it just has a lot of concepts that you just have to understand. And after you understand, we can apply these three formulas here, and you might recall them from the big five, or these are the three here, three of the big five, and these are just the most important formulas here for projectile motion. And if you get these down, then it's really simple to do projectile motion. So I hope you're excited. And alright, so let's get started with projectile motion. So what is projectile motion essentially? So what projectile motion is when there is movement or motion along two axes. So what I mean by that is, let's take an example. So here I have an example of a cannon right here, shooting a ball, and this pink ball is what we're going to consider. And so it's shooting a ball out, and and I drew the trajectory of its path. So that's a key word here. So the trajectory is going to go like an arc, right? And then it's just going to fall over at some point. And what we see here is that there is motion along two axes. So what I mean by that is, let me just erase this because I already have the trajectory. But motion along two axes is, you see that the object is moving along the x, right? So x and y axes like this. We know that the object's moving along the x, right? And it's increasing its height, or it's flying more off of the ground, right? It's getting higher off the ground. So that means it's also increasing its distance in the y direction, but until it reaches the highest point, where then we see it's coming down. So we can actually draw vectors for this at these points. So the ball here, when is just released, right? You can see there's already some kind of velocity going in the x direction, right? Because if there wasn't a velocity going in the x direction, then there wouldn't be any displacement on the x-axis, right? And also you see that there's some kind of vector along the y-axis as well, because that is causing the ball to go up, right? It's not just going straight horizontally, it's just going up, and it's going at an angle. So that means, if remember vectors, right? When we were talking about vectors, the vector sum. So that means the vector sum here would be this, right? And obviously you could use the parallelogram method or some other method, but you can see that this would be the resultant vector if you were to add vector x and the vector y in the specific directions, right? So that shows how the ball is going to travel along this trajectory path, right? Because we see that it's going to go here, and that's because of the vector sum. And at every point, right, there's a velocity x, there's a velocity y. Now, what you see that at the top is, you see that's the top, right? This is the max height, right? It can't go higher than this. So there is no y vector here, actually. So there's only just an x vector, because it's, again, it's going to continue to move along this x-axis, right? Otherwise, it would just fall down, right? It wouldn't move far past that. Now, there is continuing an x-axis, but now here, as you see on the way on its decline, I'm going to actually keep the same color. You see that the y vector is actually going down here because it's decreasing, right? It's decreasing in height. It's going down. So the y is actually this direction, and the x is still like this, right? It's still to the right, or in our case, to the right. And because that's the direction it's moving. Again, here y is decreasing, and then x is here. Now, you might see a pattern here. So we see that the x, right, the x component, we can think about it, is always constant, right? Okay, so I think we can see a pattern here, right? We see that the x component, right, everywhere we see the x component is always constant, like it's never changing. The y is changing, right? Y is increasing at the start, at the max it's 0, and at the bottom it's decreasing, right? It's decreasing, or in another case it's going in the negative direction, right? If we consider up to be positive, down to be negative, then we can see that it's going in the negative direction when it's decreasing. Now, again, coming back to the x, you see that it's always constant. And this is actually a really key thing about projectile motion. So in projectile motion, the horizontal component of velocity, so a horizontal component of v, right, it's always constant. So I'm just going to write that down here. So horizontal of v, right, vx, right, or I'm going to denote it as vx, vx being the x direction, is always going to be constant. So that is actually a really key thing, and it'll be really helpful when we're solving problems. So now let's think about it, right? So now we've always dealt with in like kinematics, right? So far in the videos, we've dealt with motion along one dimension, right? Just left or right or up and down, right? We haven't dealt with both, right? So what we're gonna do is we can't apply this to one direction. We can't apply these formulas in multi dimensions, right? So how we essentially tackle projectile motion problems is we isolate it, or we do the x dimensions and then we do the y dimensions. So all right, so how we tackle problems in projectile motion is we set up XY table. And why we do this is because, as I stated, we know that we can't do these formulas in two dimensions. We need to split them up. So it's just like splitting up vectors, how here if we were just given, as I've talked in my first or second video about vectors, if we were given this vector, right, we could split it into its x and y components, right? And we do the exact same thing here for projectile motion. So what usually happens in projectile motion is you're given an angle that this ball is launched at. So in this case, our angle would be here, and this, for example, would be theta, right? So that's the angle, and we just split into x, y components. And let's say I wanted to find delta x, I could have that in x, and I wanted to find delta y, maybe like the height, I would have it in y. Let's say I wanted to find velocity y, velocity x, I would have that in the respective areas, and then we can combine them together using vector sums, right? And remember, let's say this vector, for example, right? We have y here, and then we got x, and then this vector sum of z, I'm just going to say z, or actually better would probably be r, let's just say resultant, right? And so remember, r is always going to be, through the Pythagorean theorem, is going to be x squared plus y squared, and the square root of that will give you r. Now that's just a key thing to remember, because you'll see in the problems that we do today that will be a key factor in like solving that. So again, to review or to go back. So now we know that x is always constant, right? Vx is always constant. So since Vx is always constant, that means that there is no acceleration in that dimension or in that direction, right? So that means that if we were to, let's say, we were asked to find delta x, right? Since we know the delta x formula is VOT plus 1/2 AT, I'm just going to write it down again, just so you guys can remember. AT squared, right? We know A is 0, so that means this is going to be 0. So that means delta x is actually just velocity initial in the x direction times the time. So that's another thing that we could derive just from the fact that we know what projectile motion is. Now in y direction, right, we know, and let me just erase this xy because we don't really need it anymore. In the y direction, right, we know that, again, let's just say we would find delta y, then this would be velocity initial yt, vt, and then plus 1/2 AT squared. But think about it, y direction we talked about, acceleration in the y direction is always g, right? G as in gravity, right? So that means that this formula here for us just becomes, we just replace a here with g. So that is our gravity, and in fact it becomes 1/2, it becomes negative, right? Because g is negative, right? Because it's going down, gravity is always down. So here we would just plug in as 9.8 meters per second squared, just like we usually do, right? That was a horrible 9.8, but you get the point, right? We plug in 9.8 here as g. And so using that, we can solve delta y in the y direction. So that's how essentially you do projectile motion problems. Now we're obviously going to go over a lot of examples because we need to apply this, right? It just can't, it won't make sense if you don't apply it. But last thing I just wanted to state is, so just remember that motion along different axes, or in this case y-axis and x-axis, they're independent of each other. So they're one movement in one dimension does not affect the other movement, okay? Not necessarily, at least in the AP Physics 1, right? Does not affect it. So in that case, we need to break it up into vectors and solve like that. So now let's go on to the practice problems. Alright, so let's do this problem. So this will be actually a pretty good introduction, I think, to projectile motion type of problems. So let's first draw a picture just to get an idea. So we see that it says an object is launched at a velocity of 20 meters per second at an angle of 25 degrees. So what does that mean? So let's say this was our floor, right? And so we're saying that there's an object, and I'm just going to say ball, for example, is launched at 25 degree angle. So let's say this was the angle, and so let's just say this is the 25 degrees. And we're given that the velocity here is 20 meters per second. And let me write that a bit better. So the velocity is 20 meters per second. So what does that mean? So we know that the resultant velocity, or the velocity initial, is 20 meters per second. Now, first question wants us to find maximum height. So let's think about it, right? We want to find the maximum height. So let's say I were to draw the trajectory out, right? Let's say this was the trajectory and I landed somewhere over there. We know this would be our max height, right? We know that this is our max height. Now, how do we find this height, right? This, if I were to draw dashed lines, that would be your max height. How do we find this? So like I said, let's set this up with an XY table. So let's say X, and then let's say there's Y, right? Now, we can find the velocity initial, right, in the X direction and the Y direction. We just need to use simple trig. So what this velocity, or this along the X axis, and then this along the Y axis, the initial velocities, right? What that would be is, if you recall trigonometry, right, the velocity along the x-axis would be 20 meters per second times cosine of 25, right? Because that's just simple trigonometry. And basically, let me just explain after writing this down. So cosine 25, and what that is basically is that if we were to have a triangle like this, right, and this would be 25 degrees, and then we got this was 20, right? If you use trig, and you know cosine of 25 is x over 20, right? So that means x is just 20 into cosine 25, right? Just simple trigonometry. And same thing for the y-axis, right? That would be, let me just write that down. That would VOY, or V initial y, would be 20 times sine 25, right? Just sine and cosine, right? Basic trigonometry, which you're gonna encounter a lot in actual projectile motion, right? Okay, so we got initial, right? Now, we do recall that at the top, at the max height, right? Remember how we only had one vector, and that was x, there was no y vector? What that is saying is that at the max height, we have no y velocity, right? Because we're not going to increase in height, right? Because that is the max height, right? That wouldn't be the max height if we were going to increase. So that means there is no y velocity at the max height. So the velocity in the y direction is 0 meters per second. So now, taking that into account, what we can do is we can use our Vf squared equal to V initial squared plus 2a into delta x, right? Or in this case, delta y. That is the height that we're trying to find. So how can we use this? We only use y values. We don't use x values. We don't combine values. We just use y values. Now we know in the y direction, at the max height, we have the velocity is 0 meters per second. So this essentially becomes 0 squared, which is just 0. Now V initial, which is 20 times sine 25, and if we were to use a calculator and find that out, right, 20 times sine 25, it would be 8.45 meters per second squared, right? And now we know acceleration in the y direction is gravity, so it's going to be 2g delta y. Now we're just trying to solve for delta y, right? Because that is at the max height. So we're basically comparing the pathway till this arc right here, right? And we're using this as our final velocity point, right? And we can do that, right? Because it's projectile motion and we're using y direction. And it's just like normal one-dimensional motion here, because it's just we're only doing the y axis. So let's just solve for this, right? So delta y would be, it would become, since 0 squared is just 0, right? And so this would be negative 8.45 squared over 2g. Now remember, gravity is going down, so this is also actually negative. So the negatives will cancel out, and then we'll get our maximum height, right? We just need to plug it into a calculator, and we would get that it should be 3.64. That's what I just plugged in my calculator right there, and then I got 3.64. So that is our max height. And you see that we just used an XY table and didn't even take that much work, right? We just knew our concepts of how at the max height it's 0 meters per second. We know the initial velocities, and then we can use one of our kinematics equations to find the max height. Now let's go to B, part B. All right, so part B, right? So it's asking for the total flight time. And again, it gives a brief description if you don't know what that means. It's launch and touching on the ground. So what it's basically saying is, how much time does it take for me to get to the start, to the end, or when it hits the ground again, right? So that's what we want to find out. Now, we want to find the time. So again, let's do that same step where we split into x and y table, right? And then basically here, again, we know our v initial, right? Again, just simple trig like last time. And I erased it last time, but you get the point, right? I'm just going to write it down again quickly as possible. So 20 sine 25 is y velocity initial. Now, what it's saying is that at the end we were at 0, or we were at the end, right? And we hit the ground. So what I meant by 0 is that means our y, our change in y, was 0, right? Because we ended up, our y displacement in the y direction never changed, right? We started at 0 and we ended up at 0. So we can use that fact, right, that our displacement in y direction is 0. We can use that fact to find time. And well, how do we do that? We use our delta y, or in our case delta y, right? VO yt plus 1/2 at squared. And remember, a will be our g here because we're talking about y direction. So, and this will actually become negative, right? And I'm just going to have positive plus right now, but now let's work through it. So we got 0 here. We got 20 sine 25, right? Or in other words, 8.45 t. And then here, right, we got, we know 1/2 a, or in our case, it's going to be g, right? So that basically means that this is going to be negative 4.9 and 4.9 t squared. Now, how is negative 4.9? Because remember, gravity is always acting downward, in the downward direction. So that g, which is 9.8 meters per second squared, right? That g is going to be negative now. So that meaning, so 1/2 of 9.8 is 4.9, and then it's negative, so it's negative 4.9 t squared. Now you might think, oh no, it's a quadratic. A lot of people hate quadratics. Well, and sometimes in projectile motions you're going to experience quadratics, but this one is actually very simple. Because since it's just equal to 0 and we have no constant value, right? It's not like +2 or something where we have to solve a quadratic. We can just factor the t out, right? We just get t, and then we get negative 4.9 t plus 8.45, right? And doing so, we can solve, we see that t is 0 here, and then we'll get another solution, which is negative 4.9 t is equal to negative 8.45, and then t will give us 8.45 divided by 4.9, so that gives us around 1.72 seconds. Now here you might be wondering, okay, we got 2 answers for time, and that makes sense, right? Because we got a quadratic. Now why do we get 2 answers for time? And the reason behind that is, let me actually write this a bit neater. It looks like 122, but it's 1.72. And the reason behind us getting 2 answers is, think about it. We start off at 0. So this is where we get this t equal to 0, because at t0, we're at the initial point, we're at the starting point. And then when you hit the ground, it's 1.72. So that's how it makes sense, because this is our starting point, right? I'm going to denote that by S. It's our starting point. And at the end, when we hit the ground again, we're at 1.72 seconds. So that's how much total flight time it took between launching and hitting the ground. Go on to part C. Okay, so now we're asked what the horizontal range is. Basically the horizontal range meaning that how far did it travel in the x direction. Now here we're gonna split into xy, right? Remember, xy as usual, and we know our vx, we know our v initial y, and you might be thinking, why did I write vx here and not v initial y? Well, remember, this is just a training point, right? This is just to train you guys. So remember that the velocity in the x direction is always constant, right? Remember that from projectile motion. That's how it works. So that's why I didn't write vx, but again, vox, vx, they'll all be the same because it's always constant. So velocity in the x direction is always constant. So 20 cosine 25, again, this is 20 sine 25, which we got as 8.45, but we don't really need that here. Now remember, it's asking displacement in the x direction. Now, if we remember our formula, which is vox, right, t plus 1/2 at squared. Now remember, since, like I said, velocity in the x direction is constant. What does that mean? Our acceleration is 0 because our velocity isn't changing. So that means this is 0. So that means we got displacement in the x direction is just vox times t. Now remember, recall t we got from the last problem where we got t was 1.72 seconds. 1.72 seconds. So now we just really need to plug everything in, right? So 20 cosine 25, which is actually, let me plug it into the calculator, and 20 cosine 25 here is 18.12, and times 1.72, which should give us 30, which gives me at least 31. I'm just going to round it to 2, right? 31.2 meters, right? And so that is our basic, that is like the change in the x direction, or the displacement in the x direction. So that is our horizontal range of the object. Now, let's talk about part D, right? I'm just going to combine it here, and then let me just erase these points, right? Now, it's asking us to basically find the magnitude of the velocity just before it hits the ground. So what do we really want? We want v final, right? Now, you have to think about it. It's saying velocity, right? It isn't saying y direction, y velocity, or x velocity. That means it wants the total vector, the vector of this degree, right? It wants it to be, it wants the vector. So we need to take velocity of x at the final point and velocity of y at the final point, and find their vector sum, right? Or just squaring them and square root, right? That will give us our final velocity. I'm just writing that down here because this is actually very commonly asked. So how do we do this? We have our Vx, and as I said, Vx is constant. So again, we already just got the Vx part. We only need to worry about Vy because this is never changing in projectile motion. So now we need to find V final, right? And at the final point, right, we have delta y is again 0. So what I'm going to use is actually V final squared is equal to VO initial y squared, right, plus 2, and this is going to be, I'm going to write A, but it's actually going to be G, right? And we got delta y is 0, right? And actually, you might be thinking, okay, this looks like the right way to do it, but wait, if the final y is 0, then how is this going to work? Well, actually, this is not a right way to do it. Let's just think about it, right? So we know that here, we could use that formula, right? But you need to be conceptually sure that you're getting the right answer. So what we're basically, well, how you can find velocity final is, again, let's think of another formula, right? VO, V initial y plus AT. Again, we see that V initial, again, is 9.8, right? And it takes 1.7 or 2 seconds to hit the ground. And that we can use that, right? So initial, again, V is just going to be, it's going to be 8.45, which we got. Now, here actually, we got to be careful. So we know acceleration due to gravity is 9.8, right? But since it's 9.8, it's also that gravity is going down. So since gravity is actually going down, what we're going to see is that it's basically going to be negative, right? 9.8 times 1.72. And then in that case, we get V is actually pretty much the same thing, but negative meters per second in the y direction. And that's why I actually didn't use the other formula. And why is that? Because if we were to do this, right, VA squared, VO initial, not that this is wrong, right? This is perfectly fine. But sometimes, since we know that at the end, the y at the end, right? Oops, I should write y here. At the end, we know it's 0, right? So it just cancels out, right? Because, and then that means that initial is equal to final. But we need to remember that it's in the negative direction. Now, in this case, this works, right? Or in this case, you might have been confused that, okay, wait, I just got a positive answer again. But even though it won't matter because we're going to square it and it's going to turn into positive regardless, we just need to be clear that it's actually negative. And why do we need to be clear? Because V final, right, this is going down. This isn't going up, right? If you were to just say V final and someone asked you and you just said 8.45 meters per second, well, that would be wrong, right? Velocity final is not just positive. It has to be negative because it is going down. So again, as I stated, we got our final velocity, we got our initial. So all we're going to do is just take Vx squared, right, Vy squared, just plug it in and just take the square root of that, and we get 20 meters per second. Now that's actually wrong. Again, what did we just talk about? That the gravity is down and it's asking at when just before it hits the ground. So that means all the velocity is downwards. That means our final velocity is actually negative 20 meters per second. So here in this example, we saw how direction really matters and how we need to be clear about what point we're at, or what point the ball is at, or what point the object is at, and we need to be clear about what direction we're going. So be careful and be, as I said, just know what direction you're at and what direction the ball is going. Alright, so one last thing, right? We got that velocity is negative 20 meters per second. Now, remember to look back at the question, right? It's asking magnitude. And what the magnitude of a vector is just the value, right? We talked about this before. So velocity is negative 20 meters per second. So if it were asked if this magnitude word wasn't there, it would just be negative 20 meters per second, right? Remember your direction. Now, since it's asking magnitude, it is just 20 meters per second, right? So just be clear, right? As I stated, the magnitude of velocity, just the value, but actual velocity, you need to give the direction because it is a vector. And here actually, I wrote negative 20 meters per second, right? That actually sometimes might not be good because I'm denoting that my top is positive and my bottom is negative. Going down is negative. But sometimes you might just want to write 20 meters per second down, and that will also be right. So that's just a tip to add on. So I hope you enjoyed this video. This was just one practice problem that we went over. Next video, we're going to go a lot more, and we're just trying to get better at it, and we're just going to use these formulas, right? So again, please like the video, subscribe to the channel if you already haven't, and let me know in the comments, right, if you're enjoying these videos. If you think we need more practice problems or I just need to explain more, let me know in the comment section below. I'll take that feedback and I'll improve these videos. So anyways, thanks for watching. Hope to see you soon.